Hi, in this video we will learn what is an orthogonal set of vectors. Remember that before we called two vectors, so vector v1 and v2 are orthogonal if we find the dot product of these two, you get 0. Now we want to extend this definition for not just two vectors, but set of vectors. So this is the new notion. A set of vectors v1, v2, well, you can choose any number of these vectors. It can have any number of vectors. And it can be in any Rn, is called the set, not just two vectors. The set is called an orthogonal set if you choose any two different vectors from the set, they are going to be orthogonal. So if any two distinct vectors from the set are orthogonal. So it means that you pick any vector vi and pick any vector vj. Well, you have to make sure that those are not the same thing, same vectors. When you dot product, you need to get 0. Such a set is called an orthogonal set of vectors. Well, a very good example of orthogonal sets is the standard basis. Remember the standard basis E1 up to En in Rn, well, these are vectors, is an orthogonal set. Well, remember what were EIs? EI is, well, everything is 0. At the ith position we have 1, everything else is 0. And, well, EJ is 0, 0. At jth place you have 1, and the rest is also 0. Then when you dot product EI to EJ, if I is not equal to j, then you will see that while everything, either you multiply 0 to 0, or you multiply ith position to ith position of this ej, which will be 0, and or you multiply jth position of ei, which is 0, to these are product of 1, and then everything else is 0. So this obviously will give us 0 for any I and j which are not the same thing. Yes, this is very important. You have to pick distinct vectors. Well, to do get used to this notion a bit more, we do some more examples here. Let's check these ones. Which one of these sets are an orthogonal set? Okay, what we need to check is that we have to, so let me call this one v1, v2, and v3. We have to check if v1 dot v2, v1 dot v3, and v2 dot v3, these three dot product must be equal to 0. Yes, let's check. So 1 times negative 6 plus 2 times 3, Well, this is 0. That's nice. And I have v1 times dot v3. This is 1 times negative 2 plus 2 times 1. This is also 0. So far, so good. How about the v2 and v3? So negative 6 times a negative 2 plus 3 times 1. This will give us 12 plus 3, which is 15, and it's not equal to 0. So that means that the set is not orthogonal set of vectors. So all pair of distinct vectors, when you dot product, you get 0. Okay, let me make a bit more space there. For this one, again, we have v1, v2, v3. These are just namings. I can choose anything you like. I have to find v1, v2, v1, v3. Any pairs of distinct vectors in the set, we have only 3 of those. Okay, here. 1 times negative 1 plus 2 times 1 plus negative 1 times 1. Well, this is 0. Nice. v1 and v3, this is 1 times 3 plus 2 times 0 plus negative 1 times 3. This is again 0. Nice. v2 dot v3 is negative 1 times 3 plus 1 times 0 plus 1 times 1 times 3, and this is also 0. So all 3 pair of distinct vectors are orthogonal. So yes, this set is an orthogonal set. And the last example here, v1 and v2 is this, and v3 is that. So we want to find dot product of all pairs of distinct vectors in this case, and all must be equal to 0. So you have 1 times 3 plus 0 times 4 plus negative 1 times 3 plus 2 times 0. So this is 0. 1 times 4 plus 0 times negative 3 plus negative 1 times 0 plus 2 times negative 2. This is 0, this is 0. 4 minus 4, this is again 0. That's nice. And v2, v3, 3 times 4 plus 4 times negative 3 plus 3 times 0 plus 0 times negative 2. And this is 12 minus 12 plus 0, which is 0. So this set is also an orthogonal, yes, orthogonal set. Well, we will work with these sets a little bit more. You will see that when we have a basis which are orthogonal, then that basis will have nice properties that we will study later in another video.